I am Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today, our topic of discussion in this video is internal field in solids. So, talking about internal fields in solids, I think first we should get familiar with dielectric materials. Already, I have one video. In that video, I have explained in detail about dielectric material. Just we'll try to recollect about those dielectric materials. When we talk about those dielectric materials, so when we take dielectrics, so here when we talk about these dielectric materials, generally we'll say that these dielectrics, they are insulators, they are good insulators. So first point that comes to our mind is they are good insulators. Then in what way they are different from other materials. So when we talk about, of course, we have our insulators where we don't have free electrons and where electrons are very tightly bound to nucleus. So when we talk about dielectrics, they are a little bit different from normal insulators. What we'll observe here is when we talk about dielectric materials, once we apply external electric field, then this dielectric materials, they have this property of getting polarized. So these materials, they get polarized. So they get polarized when placed in, so when they are placed in external electric field. So we are saying that dielectrics are good insulators and they get polarized when they are placed in external electric field. Now, if we try to recollect what exactly is this phenomena of polarization, we know that when we want to apply electric field to a dielectric material, so what we'll do, we'll take a dielectric material and if you want to apply electric field, then we'll keep it in between the two capacitor plates and then we'll apply electric field. So generally we cannot take terminals of external electric field or the voltage and just directly connect it to dielectric material. So generally what we'll do, we'll take dielectric material and we'll keep it in between the capacitor plates and then we are going to apply electric field. And what we are going to observe here is capacitance of a capacitor. When we insert dielectric material, it is going to change. Okay, compared to capacitance of same capacitor when there is air in between the capacitor plates. So these dielectric materials, they have this property of changing capacitance of a capacitor because these dielectric materials, they also produced or they also get the polarized charges on the plane surfaces of them. So that's why they are going to change capacitance of a capacitor, because we know that capacitance, it is completely dependent on charge. And here also we have induced charges developing on the plane surfaces of dielectric. And when we take, suppose when we have taken dielectric material, so this is a dielectric material and we have kept it in between the capacitor plates. So this is a dielectric material. Now, once we apply electric field, first what we'll observe here is on the surface of this capacitor plates, this capacitor plate, it will become positively charged, whereas this capacitor plate, it will become negatively charged. And because of effect of these charges which are formed on the capacitor plates, what we are going to observe here is there will be separation of charges within the dielectric material. And as you can see here is, and in which direction those charges are going to move in dielectric, what we are going to observe here is, when we just look at the dielectric material, all the negative charges, they move in a direction opposite to field. And whereas all positive charges, they move in a direction same as field. So all the positive charges, they move in the direction same as field. So as we know that this is the direction of electric field. So what happened to positive charges? Positive charges, they are attracted towards the negative capacitor plate, and negative charges, they are going to get attracted to positively charged capacitor plate. And because of that, we'll observe that all the positive charges, they move in the direction of electric field, and negative charges, they are moving in the direction opposite to field. And because of this separation of charges, we are going to notice that there is formation of dipoles throughout the dielectric material. And of course, this process, it is called as electric polarization. And when we talk about different types of dielectric materials, we have seen that we have polar as well as non-polar dielectrics. But one thing what we have to understand here is, whether we take non-polar or polar dielectrics, both of them, they are going to exhibit polarization, or they are going to have net dipole moment, electric dipole moment, only when we place them in external electric field. So when we talk about different types of dielectrics, of course, we have two types. So one will be polar dielectric and other one is non-polar dielectric. So we have polar as well as non-polar dielectric. And when we talk about non-polar dielectric, it generally occurs in materials which consists of monoatomic molecules. So here they consist of monoatomic molecules. And if we try to take examples of these monoatomic molecules, so if we try to take this example, we have H2 and then we have Cl2, okay, right, O2, and then even we have our carbon dioxide and so on. And as you can see, if you look at this hydrogen molecule, it consists of similar hydrogen atoms. And when you take, suppose when we are taking this hydrogen molecule, in hydrogen molecule, we know that two hydrogen atoms, they'll come together and they'll form single covalent bond. So two hydrogen atoms, they'll come together and they will form single covalent bond, and there will be no separation of positive and negative charges, because they are bonded to each other by the strong bonding by sharing single pair of electrons. And because here also one more thing we can take in order to understand non-polar molecule is, generally we are saying that they are monoatomic, and when we talk in terms of the atom, if we take atom, we know that we have positively charged nucleus, and this positively charged nucleus, it consists of electrons distributed in various orbits. So here we have positively charged nucleus, and then we have electrons distributed in various orbits, and this distribution of electrons in various orbits around the nucleus, it is taken as a spherical electron cloud. So when we talk about an atom, that atom will take it as positively charged nucleus, and of course it will have spherical electron cloud, and centers of this positively charged nucleus and spherical electron cloud, because they are at the same point, we will say that there is no separation of charges, because center of gravity of positive charge and center of gravity of negative charge, they are occurring at the same point. And because there is no separation of this center of gravities, that's why we'll say that they are not in the state of polarization. There is no electric dipole. So that's why there is no dipole moment associated with non-polar dielectrics. And we know what is the electric dipole. So when we talk about electric dipole, we have two equal and opposite charges separated by a small distance. And the distance, either we can take it in terms of small r, and also we can take it in terms of small d. And when we have such a dipole which is separated by two equal and opposite charges, then its dipole moment, it is taken as product of charge into distance between two charges. So this is about the non-polar dielectrics. Okay, so these non-polar dielectrics, as I said, their molecules, they are not in the state of electric dipole. But whereas when we take polar dielectrics, even if we don't apply external electric field, so in polar dielectrics, what we are going to observe here is, suppose I have taken a hydrogen chloride molecule. This hydrogen chloride molecule, I think it belongs to polyatomic molecule. So it belongs to polyatomic molecule. And if we take this hydrogen chloride, this hydrogen and chlorine atom, they'll come together and they'll form hydrogen chloride molecule. But we know that of these two atoms, this chlorine, it is highly electronegative, so it will try to pull this chlorine, this pair of electron towards it, and because of this chlorine, it will gain a partially negative charge, and this will gain partially positive charge. And as you can see, this hydrogen atom, it will act as positive end of dipole, and chlorine atom, it will act as negative end of dipole. So already they are in the state of dipole. So each molecule, it is going to have net dipole moment. So that's why what we are going to observe here is polar dielectrics. Of course, without applying external field, each molecule, it is in the state of polarization. But Here, problem in polar dielectric is all these dipoles associated with each molecule, they are oriented in all possible directions, or we can say that they consist of randomly oriented dipoles. So that's why net dipole moment of entire dielectric will be zero. So that's why in order to go for this polarization in polar as well as non-polar, we have to apply external electric field. So this is just about the concept of polarization process and electric dipole process. Now coming to our topic, which is internal fields in solid. So when we, what exactly is internal field in solids? And this, what is the other name for internal field? This internal field, it is also called as local field. So here also we are going with the concept of taking a dielectric material and applying electric field. So when we apply electric field to a dielectric material, of course we know that polarization takes place. So what is polarization? Polarization is separation of charges. And here now we are going to see that within the dielectric material, suppose if I select one point or if I select an atom inside the dielectric material, then what we are going to observe here is, because of this polarization, there is some field being present at an atom or at a particular point selected inside the dielectric. And that electric field at one particular point inside the dielectric, it is not just made up of one type of dipole formation, but it is made up of many sets of dipole formation. And if I try to consider that different sets of dipoles being formed, and then total electric field at that particular point, that is called as internal field in solids. So here, in order to know about this better, if you look at this figure, so in this figure, what we have done, this is our dielectric material. So this is our dielectric material. And this dielectric material, what we have done, we have kept it in between the two capacitor plates. So when we have kept it in between the two capacitor plates, and then we are applying electric field, and then what is the direction of this electric field? This is the direction of electric field. And we know that because of this electric field, polarization takes place. But here, as you can see, what we are saying here is, due to this polarization, various sets of dipoles are formed. So here we are saying that once we apply electric field to a dielectric material, and because of polarization, various sets of dipoles are formed. And if I consider an atom inside the dielectric, suppose this is a dielectric material and I am considering one atom. Suppose let us say that atom, it is at point A inside the dielectric material. Then total electric field at an atom inside the dielectric, it is sum of electric field due to all such dipoles. It is sum of electric fields due to all such dipoles. And how these dipoles are formed? These dipoles are formed because of application of external electric field, and of course due to phenomena of polarization. And this total electric field, it is called as local field or internal field. And to understand it much more better, now we are taking help of this dielectric materials. Now for that, first what I am doing, I am going to draw this figure separately by taking one by one field, so that it will be of better understanding. So what we are doing, we are taking a dielectric material. So here this is our dielectric material. And then we have kept it in between the two capacitor plates. So we have kept it in between the two capacitor plates, and this is the direction of electric field. So once we apply electric field to this dielectric material, what is the first step going to happen? First step is, we'll have formation of charges on the capacitor plates. And because this capacitor plate onto the left, it is connected to positive terminal. So obviously what charges will be developed on the capacitor plates? Here we have formation of positive charges. And whereas on the right capacitor plate, because it is connected to negative polarity, so there will be formation of negative charges here. So positive as well as negative charges, they develop on capacitor plates. Now as you can see here, there is separation of charges or there is polarization because of formation of charges on the capacitor plates. And because of this separation of charges on the capacitor plates, there is one electric field being developed, and that electric field we are denoting it as E naught. So what is our E naught? E naught represents electric field. And what we are trying to do, we are trying to find what is the electric field because of application of external electric field. And for that, we are selecting one point inside the dielectric material. So this can be a point or it can be an atom at this point A. So when we talk about this point A, so if I try to find what is the electric field with respect to an atom that is present inside deep of dielectric material, and if I take that atom to be at location point A, because of formation of charges on the capacitive plates, what is the electric field? I am saying that electric field I am considering it as E naught. So this is the first electric field because of externally applied electric field. Now next what will happen because of this charges being developed on capacitor plates, there are induced charges, okay, charges which are by force formed. There are formation of induced, or we can also call them as polarized charges on the plane surfaces of dielectric. We know that inside the dielectric, what will happen now? Now all the positive charges, they start moving in the direction same as field. Then all negative charges, they start moving in a direction opposite to field. So now here also we can make out that there are separation of charges which are occurring on the plane surfaces of dielectric. Now let us suppose that electric field due to these polarized charges on the plane surface of dielectric, let that electric field be EP. So now, till now we have discussed two types of electric field being formed. One is because of development of charges on the plane surfaces of dielectric, and second one is because of development of polarized charges, okay, on the plane surfaces of dielectric material. One on capacitor plates, other on plane surfaces of dielectric. Now, as what exactly we are trying to find what is the net electric field if I consider one atomic position inside the dielectric material. So to get this value more specific, so for that what I am doing, let us assume that around this atom A, let there be one sphere. I am assuming one sphere. So let us assume that there is one sphere around this atom, about which we are trying to find what is the electric field developed. So have imagined one sphere here. Okay, so this is, and this sphere we are calling it as spherical cavity. So this we can call it as spherical cavity, and this spherical cavity, let us assume that it is of radius r. So this spherical cavity, let us assume that it is of radius r. Okay, and when we are taking this sphere, when we are imagining one sphere around this atom, we have to take this sphere in such a way that this radius r, it is very, very small compared to dimension of dielectric. So it means that our imagined sphere, it should be very, very small, which is surrounding our atom A. So here we have imagined a sphere, and this sphere radius, it should be very small compared to entire dimension of dielectric, but still the sphere, it should be made up of many atoms and molecules. And what we are going to observe here is, now because of polarized charges on the plane surfaces of dielectric material, because of polarized charges on the plane surfaces of dielectric material, there will be formation of polarized charges on the surface of this imagined spherical cavity. And here also what you are going to observe here is, because here I have negative polarity, so all the positive charges, they come onto the left side. So here all the positive charges, they come onto the left side on the surface of sphere whose radius is r, and the sphere is imagined around the atom A, about which we are trying to find what is the total electric field. So here obviously onto the right side of surface of this particular sphere, we have formation of negative charges. So now there is one more electric field developing, and this electric field is due to polarized charges which are developing on the surface of the sphere of radius r. And let us say that this electric field due to such polarized charges, let us denote it as ES. So what is our ES now? ES is electric field due to charges, due to polarized charges which are developing on the surface of imagined sphere around the atom A. Okay, and then as we said that this sphere, it is made up of many atoms and molecules, and each atom or molecule, because let us suppose that because of this external electric field they will be in the state of a dielectric material. So what we are going to observe here is, inside the dielectric material we have atoms and molecules being in the state of polarization, or they will be in the state of a dipole. So you will have the sphere being or it is consisting of all electric dipoles, where each atom and molecule, it is in the state of polarization. And let us suppose that electric field due to all such dipoles, it is taken as EM. So what is our EM? EM is electric field due to dipoles that are present inside the imagined sphere. And why these dipoles are formed? Let us suppose that because of the induced charges on the surface of imagined sphere. And then why induced charges are being developed on this surface of sphere are because of development of charges on the plane surfaces of dielectric. And why we are getting charges on the plane surfaces of dielectric? Because of formation of charges on the capacitor plates. And why we are getting of course, charges on the capacitor plates? Because of external electric field. Okay, and then here what we are going to, of course, as you can see, if we try to compare with the figure which we have taken in this slide, as you can make out that what is E naught? E naught is because of electric field on the plane surfaces of capacitor plates. And what is EP? EP is, of course, its direction. So E naught direction, it will be same as applied electric field, but EP direction, it will be opposite to applied electric field. So it is in this direction, and it is because of polarized charges on plane surfaces of dielectric. And then this is our imagined sphere surrounding an atom A, and this electric field due to ES, electric field due to charges on the surface, we are denoting by ES, and of course EM, it is because of dipoles inside the imagined sphere. So here we have considered 4 different electric fields due to polarization. And electric field, so net or total electric field at this atom at point A, it will be combination of these 4 different electric fields, and this total electric field is nothing but our local field or internal field. So we have taken what is the definition of local field or internal field. As you can see here, if you look at this slide, so what we have done in order to find this local field or internal field, we have imagined a spherical cavity around the atom A inside the dielectric. Okay, so we have imagined, then this point is very, very important. Then how we can take this internal field at point A? This internal field at point A, it is denoted by EI. So EI denotes internal field. In some books, this EI, it is also given as E local field. So it can be represented in any way. So here in this case, we are representing it as EI. And if we take this EI, as you can see here, I have written it as combination of macroscopic fields. So what do you mean by macroscopic fields? Here, these fields are because of separation of charges on application of external electric field plus microscopic fields. So what are these microscopic fields? These microscopic fields which are taking place at very small dimension. And what are the microscopic fields which are taking at the small dimension? Here we have imagined a very small sphere because its radius is very, very small compared to entire dimension of dielectric material. And of course EM. What is EM? EM is electric field due to dipoles, or where polarization is taking place at atomic or molecular level. So here, as we know that this internal electric field, it is combination of macro as well as microscopic fields. So of four fields which we have discussed just now, which fields will come under microscopic fields? We know that E naught and EP. What is E naught and EP? E naught is electric field at point A because of charges on the capacitor plates. EP is electric field due to polarized charges on the plane surface of dielectric. So their combination, they will give you microscopic fields, and second one is microscopic fields that are due to because of polarized charges on the sphere and because of dipoles or molecules that are present inside the sphere. So they are given by ES plus EM. So this is our internal electric field. Now if we try to simplify this internal field further, so we have taken this internal field as combination of these four fields. So if you want to you can check out here. So what is E naught? E naught is electric field intensity at point A due to charges on capacitor plates, and EP is electric field intensity at point A due to polarized charges on plane surface of dielectric, and ES is electric field at point A due to polarized charges on the surface of imagined sphere, and then EM is electric field intensity because of dipoles inside the sphere. But we know that this applied external electric field is nothing but combination of electric field due to charges on capacitive plates and electric field due to polarized charges on the faces of dielectric. So this we are going to substitute in this equation. If we substitute, and apart from that, one more point what we have to consider here is, suppose our dielectric which we have chosen, it's a non-polar dielectric. So if it's a non-polar dielectric, we know that, of course, we can take it as cubic structure. We know that when we take non-polar dielectric, here there is no possibility of formation of dipole within each atom or molecule. So what we are going to observe here is, because we are considering microscopic fields which are generated not under the influence of external electric field. And we know that when we take non-polar dielectrics, they are symmetrical in nature, where their center of gravity coincide, so they are not separated by a small distance. So because we are not taking into consideration external applied electric field, so here they are occurring without external electric field. In case of non-polar dielectrics, it consists of non-polar molecule, and each molecule of non-polar dielectric, we know that it has symmetrical structure, and center of gravity of positive charge and center of gravity of negative charge, they coincide, so there is no separation of their center of gravity. So that's why they are not in a position of dipole. So that's why here, because there is no separation of charges, so dipole moment is 0. So obviously EM will be 0. So here what we have to now substitute in this equation, in place of E naught plus EP, I have to substitute E, and here electric field due to dipoles inside the sphere EM, I have to take it as 0. So what is our final expression for internal field? Final expression for internal or local field is E, where E is external applied field, a magnitude of external applied field, and of course ES. ES is electric field due to polarized charges on the imagined sphere whose radius is R. Now, in order to find this internal field, we know E. What is E? Is external electric field. I can measure it, I can know its magnitude. But what we need to find is, we need to find what is the electric field because of polarized charges on the surface of this sphere. So our next step in order to complete this process of calculating internal field is, we need to find what is ES. Now we are going to get expression for ES, and of course this whole total process, it was done by Lorentz. So this whole process, it was done by Lorentz. So that's why we can also say that this is Lorentz method of calculating electric field due to polarized charges on the surface of imagined sphere. Okay, so our next step, because as we have seen that internal or local field, so this internal or local field, it is combination of external electric field applied plus, of course, electric field due to charges on the surface of the imagined sphere. So we know value of E, we can find its magnitude, but we need to find ES, and this whole process, it was done by scientist Lorentz. So this method, it is also called as Lorentz method. Now, if we try to look back at this figure, now what is our ES? ES is because of these charges on the surface of the sphere. So what I'm doing in order to find the value of ES, I'm just taking out that sphere separately. I'm taking magnified view of that imagined sphere. If you look at this figure, I have taken, this is our imagined sphere. Just I'm talking about this white region, which is a sphere. This is our imagined sphere, and we need to find what is the electric field because of charges developing on the surface of the sphere. Now, in order to find this, so first, now I'll try to draw this figure separately for an understanding sake. So I'm drawing this sphere again. So I'm trying to draw this sphere a little bit bigger so that we can understand its calculation. Now this is our imagined sphere, and on this sphere we have development of charges. On to the left we have positive charges, and on to the right we have formation of negative charges. And what is the direction of electric field applied? So this is the direction of electric field applied. And then now what we need to find value of ES. What is our ES? ES is electric field due to polarized charges on this sphere whose radius is R. Now what I'm going to do here is now how to find electric field. So in order to find the electric field, first what I'll do, I'll try to consider a very small area, or you can also say that very small strip. I'll take one small strip which is running around the whole sphere, and I'll try to find what is the surface area of that small strip which is selected on the surface of the sphere. And the second step is I'll try to find what is the like charge distribution on this small strip which is imagined on the surface of the sphere. And then next I'll try to find what is the electric field because of this charge distribution on the small area. And if I want to know what is the total electric field because of charges on the entire surface of sphere, then I have to integrate it. So this is the step what I'm going to follow here. So for that, what I'm doing on this particular imagined sphere, first I'm selecting a small surface area. So here, let us select the small surface area like this. We can call it a small strip also. So this is a small strip or small area which is taken on the surface of the sphere whose radius is R. So here, so as you can see in this figure, now what I am doing here, so suppose this is our point A, and this point let us call it as P, and this point let us call it as Q, and here this point let us call it as R. So this is, and of course we know that what is the radius of the sphere? Radius of the sphere, it is R. So this is R, as well as this is also R. And then next, what I am doing here is I have selected a small strip, and let us say that area of this small strip, let it be equal to dA. What is dA? dA is the small area which is on the surface of sphere of radius R, and this area, it is making angle theta and d theta with the field direction. And what is the direction of field? This is our field direction. So let us suppose that this small area, what it is doing, it is making angle theta, and as well as it is making angle d theta with the field direction. Okay, so what is our first step now? Our first step is to find surface area of this small strip selected on the sphere. Now if I go by properties of this circle, now because this is I have one small strip which is running around the sphere. Suppose first if I consider this quadrant, if I take this quadrant, suppose I'm talking about the strip, if I take such quadrants, there will be 4 quadrants. So if I try to find what is the surface area in this quadrant, then what we are going to observe here is, here in this case, if I try to find what is the value of this area, if I try to find what is the value of this area in this quadrant, then what I have to do? In this case, I have to find this length. Okay, so I have to take this length, and then I have to take this sector. Actually, if I take only one quadrant, I can call it as arc. Okay, and I have to take into consideration this arc, which is making angle d theta. Okay, with respect to field direction. So that's why obviously if I try to find this area, if we try to find this area in this one quadrant, so I can take it as PQ into QR. So this is PQ into QR, and such particular area it is running throughout the entire sphere. Okay, whole circle. So I'll be coming across 4 quadrants. So 1, 2, and at the back 2 more quadrants. So that's why here I'll take it as 2 pi 360 degrees, because 4 quadrants together they'll give rise to 360 degrees. So what is the area of this surface area? 2 pi, that is which is running along the entire sphere, and then PQ into QR. Now we need to find what is PQ and what is QR. In order to find PQ, I am taking help of triangle APQ. So when we take this triangle APQ, as you can make out in the second step, in triangle APQ, I have here theta. We know that sine theta is opposite side by hypotenuse, and we know that this is 90 degrees. So side which is opposite to 90 degrees is our hypotenuse. So AQ is our hypotenuse, and what is the side which is opposite to this theta? It is PQ. So that's why sine theta will be PQ by AQ, but we know that AQ is R. So from this, what is our PQ? PQ, it comes out to be our sine theta. Now because here I am talking about this particular, now because I am taking entire sphere, so this I can take it as a sector. Okay, and this sector, it is making angle theta, and if I try to find the value of this sector, then and of course in order to find this arc length in this sector, so for that what I have to do, so we are talking about this sector AQR. So this is our sector AQR, which is making angle d theta with field direction. So d theta is equal to QR by R. So this is the formula for sector. Or simply if you want, we can also take the simple way in one quadrant, where arc length is equal to radius into angle. So this logic also we can follow here. Radius is R and angle is d theta, and this arc length is PQ. So from this, what is our d theta? D theta is PQ by R. So that is what we have done here. So we know the value of PQ, we know the value of QR. If I am going to substitute here in this surface area, small surface area, then what is the expression for our small surface area? dA is equal to 2 pi r square sine theta theta. So we are able to get surface area of small area that is running around the surface of the sphere whose radius is r. Now next step is to find what is the charge distribution on this small area. So in order to find charge, and that charge I am denoting it as dq on the surface dA. So how I am taking this charge? This charge I have taken it as normal component of polarization multiplied by surface area. Now I think already in my video I have discussed definition for polarization vector. When we go for this polarization vector, first definition which we have taken here is induced charges per unit area developed. So induced charges per unit surface area developed. So from this, what will be your induced charges? Induced charges will be polarization into surface area. Now in this case, what I am doing, I am taking normal component of polarization. So what do you mean by normal component? P cos theta into A. Now see, generally when we talk about charges, okay, in terms of the angles, then what we are going to observe here is this charges and polarization related to these charges. It has two components. So it is resolved into two components. One component is horizontal component, which is given as P sin theta. Another one is normal component, which is given as P cos theta. But as you can see here is this horizontal component, it will cancel. Why? Because its direction, it is along the field direction E. So theta is equal to 0. So what you are going to observe here is horizontal components, they cancel. So what we have is only normal components. So that's why what we are going to do in case of polarization, I am considering normal component, which is given as P cos theta into what is the surface area of that small area selected? It is dA. And already we have taken expression for dA. It comes out to be 2 pi r square sine theta d theta. So now first we have taken small area, and then after that we have considered what is the charge distribution on this this small surface area. Now next step is to find what is the electric field due to this charge dq. Let us call this electric field on the small area dA. So let it be equal to dES. And we know that generally how we'll represent electric field. Electric field, it is because of one type of charge distribution, which is Q by 4 pi epsilon naught R square, where R is distance of the charge at the point considered. So at the point, suppose I have a charge, and if I want to find what is the electric field because of the charge, and that electric field at a point which is at the distance r from the charge, this is the formula for electric field. And one thing what we have to understand here is electric field, it is because of one type of charge distribution. Okay, so this formula I'm going to take, and if I try to apply here in this case, what is our Q? Of course, this Q is our dq. And here also, as I told you, when we are considering charges or polarization, we have to consider only normal components, because horizontal components cancel each other. Their contribution is 0. So what is the normal component of charge distribution? dq cos theta by 4 pi epsilon naught r square. That is what we have done in this case. Right? And then we know what is the value of dq. Just we have taken dq as p cos theta 2 pi r square sin theta d theta. So here in this place of dq, if I substitute, and then of course I have my cos theta, and in the denominator we have 4 pi epsilon naught r square. So here there will be cancellation of few terms. Pi will get cancelled, to 1s are, to 2s are. Okay, so r square will also get cancelled, pi will also get cancelled. So ultimately, what is the formula for electric field on the surface of a sphere? Okay, surface on small surface area which is selected on the sphere. So it comes out to be P by 2 epsilon naught cos square theta sin theta d theta. Now here, so here we have selected a small area. And for that area, we said that electric field is dS, but we need to find entire value of ES. What is ES? ES is because of charge distribution on entire sphere. So for that, what we have to do in order to find electric field ES due to charges on the surface of sphere, we have to integrate this dES. And what are the limits of integration? Because 0 to 180 degrees. Why this is so? Because electric field is because of one type of charge distribution. And one type of charge distribution, they takes place from 0 to pi, not on 0 to 2 pi, entire surface area. But we consider this one type of charge distribution on half of the surface of the sphere. That's why we are taking it as 0 to 180 degrees. And already we have expression for dES. As you know, what is dES? It is P by 2 epsilon naught cos square sin theta d theta, and P by 2 epsilon naught, they are constant, so they have taken out. So 0 to pi cos square theta sin theta d theta. Now we have to integrate this. So directly I think we cannot integrate it. So for that, what we are doing? So let us suppose that in order to solve this integral, let us suppose that cos theta is equal to x. And if I differentiate on both sides, so we are going to get minus sin theta d theta is equal to dx. So here from this, what we have, sin theta d theta is equal to minus dx. And what happens to limit of integration? So when your theta value is 0, then what happens to x? If I substitute theta is equal to 0, here I'll get my x to be 1. And if I substitute theta is equal to upper limit, which is 180 degrees, x comes out to be minus 1. So now what happens to this integral? So this integral, it will become ES is equal to, so here I have ES is equal to, and here I have minus, so minus P by 2 epsilon naught. And what are the limits of integration? They are from plus 1 to minus 1. And what is cos theta x? So because here cos square theta is there, we'll have x square. And sin theta d theta, of course, minus already we have taken, so we have to consider dx. So this is minus P by 2 epsilon naught. We know that x square, integration of x square will be x cube by 3. And we need to substitute limits of integration plus 1 and minus 1. So if we substitute limits of integration plus 1 and minus 1, which we have done here, so minus P by 2 epsilon naught, if I substitute upper limit, which is minus 1 whole cube, will give you minus 1. And then lower limit is 1 cube. So 1 cube will give you here plus 1. So minus 1, it will become minus 2, and this 2 will get cancelled, and minus minus will also get cancelled. So ultimately what we'll get for ES? ES is equal to P by 3 epsilon naught. And already we have seen that what is the expression for external electric field? External electric field, it is given as E plus ES. So it is E plus ES. So if we substitute in place of ESP by 3 epsilon naught, this is the final expression for internal field or local field. Okay. So what is our internal field? Internal field, it is sum of electric fields due to various sets of dipoles which are found inside the dielectric material. And here, of course, as you can see here, this is our applied electric field. So our internal field, it comes out to be applied electric field plus P by 3 epsilon naught. It means that our internal field is greater than the applied electric field. So this is about our local field or internal field. And this field, because of various dipoles, and here also there is a phenomena of polarization. So here we try to find what is the polarization that is taking place at microscopic level. So for that, what we have done, electric field which is being calculated with respect to an atom or point inside the dielectric, we are imagining one sphere, and the whole process is to find what is the electric field due to small sphere which is considered deep into the dielectric material. So once we know that microscopic field value, then we can take our internal field as combination of macroscopic fields plus microscopic fields. So this is about our topic of discussion, which is internal field. I hope you are able to understand it. So thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.